Okay, so we've been looking at derivatives using the limit definition, and you've noticed that there's like patterns in every problem, right? You keep on doing the same thing, canceling out the same values, very, very repetitive process. Well, generally when you find something's repetitive, you end up with rules, right, to make it easier. And so this is your first look at a few derivative rules. I'm not going to go through each one explicitly right now. If you want to pause and take a look at them, that's cool. But basically they're just saying that the derivative of any constant is 0, that's here. We've got this rule for when there's a exponent where you're just going to bring the exponent to the front and subtract 1. Much easier to see in examples than in a rule. This one here is just saying that if there's a constant in front of the function, you can just leave the constant there and take the derivative on its own, multiply by the constant at the end. And then this one's just saying that if I've got two different functions, added or subtracted together, I can take their derivatives separately and add them at the end. Again, it's all stuff that is much more complicated to read than it is to see in a problem. So let's jump right to that. Actually, that's not true. Before we jump to this, I want to review a few things about exponents. If you remember, if I have x to the negative 1, this is the same thing as 1 over x. And by the same logic, if I have x to the negative 2, that would be the same as 1 over x squared. Another one, if I've got x to the 1/2 power, this is the same as radical x. If I've got x to the 2/3 power, this is the same as the cubed root of x squared. And one more example or two, if I've got x to the negative 1/2 power, this would be the same as 1 over radical x. And if I had x to the negative 2/3 power, that would be the same as 1 over the cubed root of x squared. So if any of that seems like you don't understand it, go back and watch that part again, because we're going to use these ideas a ton when we start doing these derivatives. So here are some actual derivative problems. The idea here is that this 4 is going to move to the front to give me 4x. And then I'm going to, on the exponent part, I'm going to subtract 1. So it moves to the front, and I take 1 away. So my derivative here, my f prime of x, is going to be 4x cubed. That's going to be going real fast as you do this more. This 4 is just going to come to the front, subtract 1 to make it 3. Right here I've got the derivative of a constant. If f of x is 5, f prime of x is just going to be 0. Right? That's one of our rules. The derivative of a constant is 0. And so we're going to kind of put those two things together into this problem here, where I've got 4 different derivatives that I'm going to take, 4 different functions of x. And I'm just going to take the derivative of each one separately, and then I can add and subtract. I guess just add in this case, add all the derivatives together. So for this one, f prime of x, for x cubed, that's going to become 3x squared. So 3 to the front, 3 minus 1 is 2. And then plus 4, so the constant's out in front, times 2x. So that's the derivative of this x squared part. Plus 2 times the derivative of x is just 1. And then plus 0, the derivative of 1. So if I put all this together, I've got 3x squared plus 8x plus 2. Now that's a lot faster than going through the whole limit definition on these things. Couple of trickier looking problems. When you see this, like more unorthodox looking stuff, one thing you could try doing is rewriting it into a more comfortable looking expression to start from. So I'll tell you what, I'm going to stick with one color when I'm doing the simplification. I'll switch to another color for the derivatives. So for if I'm going to rewrite this f of x, I could say this is actually 4 times 1 over x. which is the same as 4x to the negative 1 power. So now if I were to take the derivative of that, f prime of x would be negative 4, right, as this 1 comes to the front, x to the negative 2 power. And that 2 is coming from negative 1 minus 1 is a negative 2. I could then rewrite this as negative 4 over x squared. Same idea here. I'm going to rewrite this one. I've got 4t squared over 5. Well, I want to rewrite this as 4/5 t squared. And then I'm going to take this 2, bring it to the front, and subtract 1. And switch to red for the derivatives, I guess, to stay consistent. I'm going to have 8/5 t to the first power, right? 2 minus 1 is just 1. So I don't need to write that. I would just leave the derivative this way. Or, if you want, you could write it as 8t over 5. Just so that it matches more, with the form of the original. It's totally up to you. You wouldn't lose any points on a test or anything for leaving it in this form. One more here. Again, let's rewrite it before we start. So this is 2 radical x. I'm going to write that as 2 times x to the 1/2 power. So again, this 1/2 is going to come to the front, and I'm going to subtract 1. But I can't subtract 1 as it is. I have to have a common denominator, right? So I'm going to change this. Instead of minus 1, I'll make it minus 2 over 2. And then I can write my derivative, f prime of x. 1/2 times 2 is just 1, times x to the 1/2 minus 1 is negative 1/2. And so again, if I reorganize this, that's 1 over radical x. Almost out of time here. See if I can go through a few more real quick. At least this one. Here, I would rewrite this one as 2x to the negative 2/3. So this is going to be negative 4/3 x. If I subtract 1 from that, that becomes negative 5/3. And then down here, this one's actually easier than it looks. 3/2 x, the derivative of that, is negative 3/2. So hopefully that helps. I know there's a lot of quick exponents and negatives and fractions. Just, watch it a few times if you're having a hard time following.